Okay, so I think we can uh, start, right? So in the last lecture, we discussed about different tricks for achieving generalization, and there we talked about data augmentation, weight decay, um, ensemble learning, and other tricks as well, right? Early stopping. One thing that we did not discuss in the last lecture was dropout. So we did not have time to discuss about dropout as a trick for generalization, and that is what we will do today. So for today, we will start discussing on dropout. We will conclude our discussion on dropout, and then time permitting, we will start with uh, different modalities of data. And the first modality of data that we will be talking about is image based data. So naturally, we will start talking about neural network architectures that are modality specific, more or less, right? So for images, it is CNN. We will not talk about CNN, so to say, today, but we will start setting up the tone for discussing CNN. And then next lecture onwards, it will be about CNN. I think after today's lecture, we will have 3 more lectures, maybe, I guess, before the minor, right? So that should be more or less enough to cover CNN. Okay, so and that is anyway, that was always the target, to cover up to CNN before the minors. Okay, so and we are kind of on track. It might be that small portions are remaining in CNN, and that we will do after minor if that happens, and that is fine, right? So let us start, right? So lecture 11. Okay, before I start, I have one announcement. So obviously Monday the practical did not take place, right? Naturally the Viva did not take place. So that Viva will happen coming Monday. Now some of you ask me, and rightly so, that whether it will be 2 Vivas combined, Viva for practical 2 and Viva for practical 1. The answer is no. In one practical session, it is not possible to take Viva for both. So we will have Viva only for practical 1 in the coming Monday, and whenever the practical happens after that, we will have Viva for practical 2. So no, both of them will not happen together. It will be only practical 1. Okay, and obviously come prepared. I mean, do not say that I did it some time back, I forgot. Because remember that the total marks is Viva marks multiplied by whatever you are getting. And so if Viva goes bad, overall thing will go bad. So please come prepared because it is product, right? So yeah. Anyways, coming back. So in the last lecture, we discussed about generalization. Today, one trick for achieving generalization that we did not discuss was dropout. And so for most of today's lecture, we will be talking about this dropout. For most of today's lecture, we will be discussing what is dropout, how does it help, does it have any real relation to some things maybe we have discussed earlier, and so on and so forth, right? So that is the idea. Okay. So with that, let us start with dropout. Okay. So now the name dropout itself is self-explanatory to a certain degree. It is saying that you will drop out. So in dropout, what you do is you drop out certain nodes in your neural network randomly, and you do it for each update. And the idea is this dropping out of nodes randomly help your model to generalize better. So what you do? You select some random nodes, and these random nodes you are selecting can change from iteration to iteration, from update to update. Remember, iteration is equivalent to one update. So these random nodes you are dropping out can change from iteration to iteration. It will change from iteration to iteration mostly because it will be randomly done. And then from there, the idea is that because you are learning in this manner, where sub nodes are getting switched on, switched off, and switched on randomly, that stops your model from overfitting. That allows your model to generalize better. That allows your model to learn better. So, in a nutshell, that is what dropout is. It is exactly what the name suggests. You drop out certain nodes in random. Okay, and we'll see how this actually works. Right? We'll talk about that. So dropout, the broad idea is we drop certain nodes, and these certain nodes are selected randomly during training. Okay, we drop certain nodes, and these nodes are selected randomly, and we do it during training. What does dropping of nodes means? Remember, each node has an input and has an output, right? Each node will have not one, it will have multiple inputs and multiple outputs. Dropping a node means all the inputs goes away, all the output goes away. That means all the edges that are connecting to the node goes away, and all the edges that are coming out of that node also goes away. And remember, each edge corresponds to weight. That means those weights are not active for that iteration, which means those nodes will not be getting updated for that iteration. So dropping node means the edges connected to that nodes, both incoming and outgoing, they are kind of masked. If I use a deep learning terminology, we call it masking. So they are kind of masked. And what does masking means? That means those nodes are as if not there. If those nodes are not there, those are not getting influenced by nodes that came before it, and those are not influencing nodes that will come after it in the sequence of layer, not in time, obviously. Clear? What dropping off node means? It basically means that some of the parameters will not be getting updated. It means some of the parameters associated with that node, both weights and biases, will not be updated for that iteration. Okay. So this means, as I was saying, parameters associated with the nodes are not updated. Okay. Now, as this is a deep learning course, this masking term is very important. It will come again and again. It will come more when we go to CNN, right? So this masking term you should get yourself familiarized with. You should know what masking means. Masking of a node means, what masking of certain portion of an image means. It will come later. So this masking term means basically that portion you basically it stops influencing in some manner, right? Okay, so this is broadly what is dropout is clear. Broadly, I mean the details are coming, but broadly, is there any question on what we discussed till now? No. Just to confirm, it is still used in calculating the next layer. Right? The value is used in calculating, it's just not used for trading. No, in that case, it is not used. So they are as if not there. So the edges are removed, right? So if the edges are removed, that information will not pass. The weights are still there, but they are not used to. They will not be used to calculate the next layer. So it's not that just the weights are not getting updated. Those are not there for that iteration. Okay. Now, one key aspect you should keep in mind is that I have mentioned here also that this is only done during training. And at least the classical dropout is something that you do only during training. And the idea is you want the model to generalize during training itself, right? I mean, although there is a variant of dropout which is also used during prediction, but that has some other purpose, and that is known as Monte Carlo dropout, where you keep the dropout on even during prediction. But we are not discussing that. So for the course, for now at least, for the near future also, dropout you should remember is only done during training. We'll not talk about Monte Carlo dropout. If you are interested, you can read about it. If you have any doubt, you can always ask me. I'll be happy to discuss. But in this class, we are limiting ourselves to dropout, the classical one, which is only during training. Okay, so now let us try to understand the same thing, but with a diagram, right? So let's take a neural network, and let's say my neural network looks something like this. Okay, so these are the new nodes or neurons of my neural network. Now, in the classical sense, without dropout, everything is connected, everything is active, right? And I will spend some time drawing it because to show dropout, it is important that I draw it. So it's fine. Okay. So first one is 3, second one should also be 3. Third one should also have 3. And the last one should also be 3. Okay, something like this. Okay, so basically I'm drawing the full network. Okay, and there are additional nodes in the second to third layer. I'm sorry, additional edges in second to third layer. I have not drawn it, but you know that they are there. So this is the full layer, right? Full network with some missing edges in the second layer. Okay, some edges are missing. I'm not drawing it. It is too chaotic. Now, what does dropout will do? What dropout will do? So if I'm doing dropout, and I will do a high level of dropout, let's say. So during dropout, what will happen is as follow. So you have the same network, 3, 4, 3, and 1. Okay. And now dropout is triggered, and let's say 4 nodes 4 nodes in random has been dropped out. Okay. 4 nodes has been dropped out. What are these 4 nodes? I don't know, but let me mark it randomly. So let's say this node has been dropped out. Whatever is pink, magenta has been dropped out. Okay. So this has been dropped out. 4 I said, right? Maybe let us make 5. This has been dropped out. This has been dropped out, and let's say this has been dropped out. Okay. So 5 nodes, not 4. I made it 5. So 5 nodes have been dropped. So what does it mean? It means that information will pass at this layer as follows. So information will flow okay. Like this. So see the pink ones, the magenta ones, there are no edges. So there is no information that is flowing. And this is for a given iteration. In the next iteration, another 5 or another 4 might be dropped off. So it will not remain the same nodes that are getting dropped off. Iteration to iteration, the nodes that are getting dropped off will change. Clear? They will not even receive the information. No, they will do nothing. Okay, and I'll write the steps also, and that time you will understand maybe in little bit more details what is happening. Yeah. What policy do you use to choose which nodes are the dropping out? We don't choose. We just Bernoulli sample. So we don't choose this. We choose one thing, that dropouts would only happen either in the input or in the hidden layer. Dropout do not happen in the output layer because you want all the outputs. Okay, so output layer there is no dropout. That is the only choice we make. And then each of these node you can think of it as random Bernoulli sample. Now, yes. Each one independently. So each of this is independent random variable following Bernoulli distribution. Bernoulli distribution is what? Coin tossing. So let's say head means that will stay, tail means it will drop off. So for each of these nodes, you can think of like tossing a coin, and depending on the output of that or the result of that coin toss, if it is head, you keep that node. If it is tail, you say this node is not there. Okay, this node is not there for a given iteration. Next update, you again toss coin. Again, the outcome will change, right? And accordingly, the node that will get dropped off will change. Clear what is happening? Each node in the input and the hidden layer, think of it as one separate coin. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9 nodes in this case, 9 coins. You toss the coin. If you get head, that node stays for that iteration. If you get tail, that node goes away. It becomes pink. But we have to fix the number of like total. No, you are already fixing by the probability of your coin toss, right? So that each coin I said is each node I said is a coin. That coin is tossing it, but that coin it need not be unbiased. So maybe that probability is 0.2. So that means each time if you do 100 experiments, 20 times it will drop out. So that is being fixed by the coin itself. You don't do it. I mean, in this case, obviously while implementing you have to specify what is that dropout rate, but in a generic sense, the coin is taking care of that, right? So it will not lead to the underfitting because no. Why? Because it can if you start dropping out 80% of the nodes. Generally, the dropout ideal number is actually 0.5, but people generally use 0.2. I think in input 0.2, in hidden 0.5 is a reasonable number that is often recommended. So input layer 0.2, hidden layer 0.5 is a reasonable number that is recommended. If you start dropping off 95% of the nodes, it will learn nothing. So in that case, it will happen. So you have to be careful in what that probability of success you are setting. Okay, so probability of success means dropping the node, let's say. If that is the case, then that is 0.2 or probability of, so in that sense, right? So that ensures that there is no underfitting. Okay, any other question? Okay, so this is how it, what happens, what the node, the diagram will look like, right? Mathematically or algorithmically, what is happening? Let us try to write it down and see. Okay. So let's talk about the algorithm. I mean, I'll not talk about the detailed algorithm. It is more like steps. So what you do is that you initialize all the weights. Step 1 is you initialize all the weights. Okay. And how do you initialize? Based on the activation function, select a good initializer and initialize it, right? Initialize all weights. And again, I'm not writing biases, but you can always think initialize all parameters. Okay. So, I mean, for the sake of discussion, I'm assuming there is no bias in the model. Bias is set to 0, but if you want, you can set bias also. Same thing follows, nothing changes. Okay. So initialize all weights. Okay, that is the first thing. And then let's say update 1. So that means this is the first time your parameters are going to get updated. Iteration, not epoch. Okay, because mini batch, each mini batch is what we're talking about. Update 1. What you will do is drop nodes at random 100p% because BP is the probability of, let's say, dropping off. So 100p is the percentage. So, or so you basically drop off each one you select and you decide, right? P% of the nodes at random for remaining nodes nodes. Okay, 1 second. 1 second. I think remaining nodes is not the correct terminology. So for weights associated with the remaining nodes with remaining nodes, what you do is you do the usual update. So WT plus 1 is equal to WT minus eta, sorry, minus, not plus, minus eta times theta LWT. I'm writing the SGD step. If you want, you can write the Adams step, does not matter. I'm writing SGD step because I have to write 1 or 2 more less terms, but you know that this is an update step. It can be Adam, it can be RMS prop, it can be ADA grad, it can be a Nestrov accelerated gradient descent, it can be momentum based, or it can be something else. So it's basically an update. And what we are saying is the important part is that only active nodes are, active weights are getting updated, right? So forward pass is also using only the active weights, and backward pass, which is update, is also using the active weights. And this is during training. Okay. So this was update 1, right? And then you will have, after this, you will have update 2. Update 2, you will again drop 100p% nodes at random. And because it is at random, it might happen that some of the nodes that were dropped in update 1 are also dropped in update 2. It will also happen that some of the nodes that were not dropped in update 1 gets dropped in update 2. It will also happen that some of the nodes that were dropped in update 1 are not getting dropped in update 2. And lastly, it will also be happening that some of the nodes will be active in both the updates. So there are only 4 possibilities, right? Dropped in both, dropped in first, dropped in second, not dropped in either. Okay. So update 2, drop P% of nodes at random, and then you for weights associated with active nodes, what you do is the same thing. W t plus 2 is equal to W t plus 1 minus eta grad of, I mean it should be W, right? I was writing grad of theta, that was wrong. W L W t plus 1. I think here also I wrote theta, it should be W. And this will continue. Okay. And you can imagine that your model will get trained for, I don't know, maybe 500 epochs. That's a standard number. In each epoch, you will have, depending on the data set, maybe 1000 iteration. So you are talking about 1000 times 500 update. You can imagine that every node and every weights associated with node will receive some good number of updates. It will not happen that some of the nodes have never been updated. I mean, that probability is very, very, very low. That the probability that one node never gets updated in 500 times 1000 updates is almost 0. I mean, as good as 0, right? It is not 0, but as good as 0, right? Because independent, you can just do the product and find out, right? 0.2 times, I mean, 0.2 to the power 500 times 100,000, right? So it will be almost 0. Okay. So note that in the 2 updates, some parameters or weights, some weights get updated once, some twice, and some never. I mean, if I take only 2 update, this is good. This all of these 3 will happen, right? Only 2 update. But during the total training, every weight gets enough number of updates, enough with high probability. Again, we are bringing probability because the nodes are getting dropped probabilistically. So naturally, the number of updates they will get will also have to be probabilistic, right? With high probability. Any question?
Sir, why don't we do this random sampling or dropout, initially it's not the every update.
Initially, if you do, you will do only once, right?
Yeah, so that will it will reduce the computation time
But-
also for that types
but-
of sampling.
But then it will be only the same nodes that you have selected. So
I'm saying like list of dropouts like at this update.
you can do. There is no problem with that. You can do and then take it. Then you have to. It will take memory. Nothing comes for free. You will have to store it. I mean, how does time? How much time it takes for to sample? Nothing. Memory will probably be the bigger bottleneck in this case, right? Okay. Yeah.
So if we are talking about like random and considering each node at independent probability, there might be that one whole hidden layer might get dropped.
What that probability is very less. You can calculate it because you will have a very large network, right? We are talking about generalization and avoiding overfitting. Overfitting happens for a complex network. So, if what is the probability that if you have let's say m number of nodes, and out of this m number of nodes in k number of layers, let's say, and all of those happens to be in single layer, highly unlikely, right? So, and if it happens in one time, that will have nothing will get updated in that case, because if you remove this out, it is gone, nothing is updated, but that will be one iteration. So, that iteration is a waste, but that is almost impossible. I mean, not impossible, probabilistically possible, but that a very small probability, right? So, that is the scenario. Make sense? But while I'm covering this, I'm thinking this might be good question for minor and major. That find the probability that one layer will have or everything gets drop out. And maybe some dependencies I gave, and I don't know. I'm just thinking while I'm covering it. Anyways, let's come back. Okay. So this is what dropout is about. And as I said, um, we only apply dropout to input and hidden layers, hidden nodes. Dropout is not applied to the output nodes, makes no sense. Okay. So we only apply, why it makes no sense? Because then one of the output will not be there. So your loss function will get changed now. So in that sense, it makes no sense, right? So we only apply dropout to input and hidden nodes, okay, not to other nodes. And now assume that you have total m input plus hidden nodes, right? You have total m number of input plus hidden nodes. That means each one might get dropped or might stay there. And even if a single node getting dropped off is like getting a different network. So that means you are talking about 2 to the power m networks here. Although you are not never training the 2 to the power m networks separately, but in the process, it is kind of exploring the possibility space. If I mean, all the possible networks, and the possible network is 2 to the power m. Obviously, it will not explore all the networks, but a finite number out of those 2 to the power m networks will be explored in the process of training, right? So, considering m input plus hidden nodes, dropout explodes from 2 to the power m possible networks. And again, it explodes from 2 to the power m networks, but it will not reach that 2 to the power m number. It will not explore all the possibilities. It will randomly explore whatever the number of iteration is, that many possibilities. So if the total number of iteration or update is 500 times 1000, so it will explore potentially 500 times 1000 different networks from 2 to the power m different possible networks. Okay, and again it is assuming that each of the 500 times 1000 you end up getting different network, because it is possible that some of those turns out to be the same network also. I mean, that's also a possibility, right? Clear what is happening? Any question? Okay, and lastly, as I said, let me write it down also. We apply dropout only during training. Okay, and for completeness, I will also write that there is MC dropout, which also keeps dropout on during testing or prediction, but that's not what we are discussing. There exists Monte Carlo dropout, which keeps dropout on during prediction as well. So it turns dropout on during prediction, and what you do is that you predict multiple times. Because of this dropout being on, you will get different predictions. So those are like different samples. You take the mean, the standard deviation. So it's like a Bayesian or a probabilistic way of doing things. But again, this is not what we are discussing. We will limit ourselves to this one. We will limit ourselves to this one. Okay. For now, at least. Yeah. Uh, there is a problem. I mean, ultimately it will turn out to be same. I mean, ultimately it will not matter, because nodes being dropped out means edges are also getting dropped out. It's just another way of looking into things. I mean, think about it, right? Where is the diagram? Here. I mean, dropping out nodes is what I showed. I mean, that is essentially dropping out edges also. No. Why? How is it ensuring? For example, let's take the pink, right? 3 pink diagonally you can see. The middle one and the second one and the first one, right? See the 3 pinks? Those 2 edges getting dropped out means those 2 nodes get dropped out. No. Why will it reduce? Why do you think it will reduce? Correct. That is the idea. No. Think about it. Just suppose, I remove one of the edges, right? Let's say I remove this edge that you see here, right? I'll delete this one, but you can see the green dot, right? Yeah. So I remove this edge. Okay. And then, I mean, what does it even mean? Does it not mean that this node got dropped out? Other. Now come to the probability part. So you can always tune that probability instead of 0.2 over nodes, make it 0.5 over edges. You get the same thing. Because the number of edges is more, so how many edges are getting dropped off? You tune that probability, you will instantly end up with the same thing. Probabilistically, yes. Probabilistically. I'm not saying one sample will become same. That's not what I'm saying. But I'm saying this is done probabilistically, right? So probabilistically, if you draw infinite number of samples, one by dropping off edges with a certain probability and associated equivalent probability of the nodes, infinite. Remember, that's the key. Those are statistically will turn out to be same. It does not mean that one will remain same. I understand what you are saying, that it is possible that this green edge remains but the other one goes away. That's what you were saying. But then what happens is that you are passing information here, complete information, there incomplete information. and the end result turns out to be same.
Both of the, like in both cases, we are achieving that we are getting different networks.
Exactly. So it will not help. It will not help you achieve anything more. Now then, if it is not helping us achieve anything more, why don't we just abandon this and do drop out of edges? That's the natural question to ask. Now that the reason is, when you write the code, right, what is easy to maintain? Do you maintain how do you maintain nodes and how do you maintain edges? So now it comes to computational convenience. Both of these are equivalent statistically. And now if they are equivalent statistically, then you will select what is computationally convenient. Computationally, tracking node and removing them is easier than removing edges, and because edges are higher in number than nodes. So that makes it difficult now programming wise, because you also need to scale it from a programming point of view. So statistically, you can do the maths. You will obviously the p will not be same. P.2 in edges is not equal to P.2 in nodes. That will not work. But for P.2 in nodes, you can find an equivalent P for edges, which will give you the same thing. And now, if that is the case, both are same statistically. And now, if both are same statistically, so then you will choose convenience, programming convenience, and that's what you will do. Yeah.
I can do this question. Like, but for when we drop the nodes, so we have a combination of network that we are getting with our in combinations of. But if we drop edges, so then our combination of network increases because
Mm, because the number of edges is more, right? But you are now getting not a fully connected network. You are getting a network that is not fully connected. That programming that is now difficult. Also, your let's say you get to the power k number of possible networks where k is much greater than n. Possible. But ultimately, you will select 500 times 1000 network out of those in both cases. And the best case scenario is you get 500 times 1000 number of nodes in both cases. And both 2 to the power m and 2 to the power k tends towards infinite because they are very large. So the probabilistically again it comes down to be the same thing. Statistically it again boils down to the same thing, because 2 to the power m and 2 to the power k both are very large compared to this 500 times 1000. So if both are very equally large, it is like 1 by 10 to the power 7 and 1 by 10 to the power 9. I mean, essentially, practically both are 0. Right? 10 to the power minus 7 and 10 to the power minus 9, both are practically 0. That will again not matter. Make sense?
And so when you said that even in the forward and backward pass, even in the forward pass, we will not consider the weights that have been dropped off.
Right. For during training.
During
Training, not during prediction. Prediction will consider everything, and I'm coming to that next.
But even so during training, is that not something that we don't want? Like this loss function will not be a function of those weights which have been dropped off.
True.
Eventually, our test or prediction function should have all the terms.
Correct. So you are coming at a good point, which I was going to say next. You are right. What will happen is that because you are dropping off certain nodes, so there are less number of weights responsible for the same output. So the weights value will increase, and you will need to scale them. So the weights will be scaled during prediction. Each weight will be scaled to what you are saying is correct. So the weights will be scaled so that it does not matter. Okay. So the weights will be, and by the way, you don't do it because if you start taking those, then there is a factor that in your loss function that you are not getting updated for. So your update might not be adequate enough. So what I mean is, let's say this green dot, right? I take, and let's connect that green dot during the forward pass. It is possible that most of the information is getting passed through that green, right? And if that happens, then all the actual updates you are taking will tend towards no update. So to ensure that the updates are adequate, that's why you do in the forward pass also only the active ones. So what will happen if I connect this green, right? Let's say, and you can assume that it is possible that most of this Y output is highly sensitive to this green arrow. That's a possibility, right? And if that happens, it is less sensitive to the other ones. If it is less sensitive to the other ones, the gradient will be very small. So there will be almost no update. And you don't want that. So what you do, you remove it, update it, but there is a problem. Because you've removed it, eventual prediction is based on all the nodes, so you scale it. And you can show that scaling it gives you an unbiased estimator of what you are looking at. And I will show you as well. So this green dot, if you have drawn, that's fine. I am removing it because later we will not remember this discussion and this will create confusion. So I think this was connected. No, this was not connected. This was connected. Undo. Okay, let's leave undo for now. Okay. Yeah, something like this. Okay, this was wrong. Clear what happens? I'll repeat also because this was a very important point. If you, let's say, keep the inactive weights during the forward pass, there is a possibility that that path might lead to the most sensitive path, in which case the other weights that you are intending to update will have a very less sensitivity, which means gradient, which means the update will never happen or will be negligible. We do not want that. We want update. So that's why we remove it. But removing it is problematic because then removing it is problematic because then what happens is only few of the weights are responsible for the output. So the weights get scaled. I mean, they will have higher value, so you need to rescale them, higher or lower value, whatever, but you need to scale those. And that is what I was actually going to write next. There exists MC dropout which keep dropout on. And lastly, because we only only finite few, and few is a wrong terminology, I don't want to write few, because only active nodes contribute in forward pass during training, and all nodes contribute in forward pass during prediction. We need to scale the weights. Okay. Because this happens, we need to scale the weights. And how do you scale the weights? Let's call it W tilde is equal to Q times W. Sorry, not Q times, is equal to W by Q. So each of the weights that you get is divided by Q. What is Q? Bernoulli distribution 1 minus P. Q is 1 minus P, because P I am assuming is getting dropped out. So how many times it is staying? 1 minus P, that is Q. I mean, probabilistically. And so you scale it by 1 minus P. So basically you scale it by the number of times it probabilistically stayed. And each node probabilistically stayed for 0.8. If 0.2 is the dropout rate, so by 0.8. You scale it. It's kind of doing an average. It's average. I mean, ultimately we will do basically the prediction, right? And prediction, you need to show that it's unbiased. Unbiased you show by taking expectation, which is average. So ultimately, this will give you an unbiased estimator. Okay.
So what state for Q probability? This particular state for Q probability.
Yeah.
So should we not multiply 12 with 20?
Okay, I will do the derivation. You will realize because you will do expectation of the prediction, right? So because of the expectation, you will find that Q will come at the top, and that has to be cancelled out. So from there it is coming. Okay, so why is this divided by Q? Let us try to see. Okay. So if we are not doing any dropout, let's say we are not doing any dropout, then what is the prediction? So without dropout, what is the prediction? And let us take a, by the way, linear layer. Okay, we're going to take a linear layer. I mean, and so single layer linear operation and dropping out, right? So without dropout, the prediction is what? Y hat is equal to summation over I Wi xi, a simple linear layer, right? No bias. With dropout, what is the prediction? Let me write it y, okay? Because I will write t as target, so this can be y. So let's write it y hat is equal to summation over I delta I Wi xi. What is delta I? It's a random variable that you draw from Bernoulli distribution with probability that it will stay, I mean it is equal to 1 is 1 minus p, and probability that it will be equal to 0 is p, right? So where delta I is sample from Bernoulli distribution with probability q. Q I am writing here because 1 is generally the probability of success. I mean that's the notation in Bernoulli distribution. Head is generally 1. And here 1 means the node stays, 0 means the node goes away. So that is why it is Bernoulli with this parameter q, not p. Q is equal to 1 minus p, obviously. Clear what I am saying? In doubt? Remember that in Bernoulli 1 is the probability of success, and here 1 means the node stays, and that is why it is Bernoulli of q and not p, because it stays is what we are calculating, right? Now this is an estimator, right? And remember we said that this is W tilde, by the way, we have scaled it, right? W tilde is what I wrote, I guess. Yeah. Now, how do you prove that the right hand side is an unbiased estimator of the left hand side? How do you prove any estimator is unbiased? You take expectation of that, and if expectation of your estimator gives you the true things you are trying to estimate, then it's an unbiased estimator, right? So from here, taking expectation with respect to delta y hat is equal to expectation with respect to delta summation over I delta I Wi tilde xi, right? What is expectation of sum? Sum of expectation, so the expectation will go inside. Wi and xi, they are not function of the random variable as such, right? They are kind of constant because they have been already been trained and scaled. So this is equal to summation over I Wi tilde xi and expectation of delta. What is expectation of delta? Q. And now you can see what I did. And what is Wi tilde? Wi by Q. Q and Q cancels out. You end up getting Y. So it's an unbiased estimator. So you can see why we scaled it, so that we can get an unbiased estimator, right? This is equal to summation over I so unbiased estimator. Clear? Why is it scaled like this? First of all, it is clear. Taking expectation. So you know unbiased estimator. What is an unbiased estimator? Okay. So suppose I want to calculate the I want to do some survey, right? And in survey you always take small samples. You cannot survey from everyone. So you take small survey, right? And you compute some quantity. Now, how do you know from the survey, which is a finite sample survey, that quantity you are calculating is the correct quantity? Because that is like an estimate. Your sample mean is an estimate of the population mean. You're trying to do that, right? So the definition of unbiased estimator is that this sample mean or sample something, if you take expectation over that, over all possible things, if that matches the population one actually, then you call it an unbiased estimator. And that's why, do you remember the formula for sigma, standard deviation? What is the formula? X 1 by n. Some of you write n, somewhere you have seen 1 by n minus 1. Both you have seen. Why are there two? Because 1 by n minus 1 is an unbiased estimator. So when you are computing from the sample, you should not use 1 by n. You should use 1 by n minus 1 summation x minus mu whole square. That's an unbiased estimator of standard deviation. Why? Because this standard deviation, you take mean of this. It will give you the population standard deviation or variance, sorry, not standard, variance, right? But sample mean is an unbiased estimator of population mean. So sample mean is 1 by n summation xi over the sample, and that is an unbiased estimator. Because expectation of your estimator, if it is equal to the quantity you are trying to estimate, then you call it an unbiased estimator. Unbiased estimator. Okay. And that why we call it unbiased estimator? Because you can see in a mean sense, your estimation is matching the true. And in the mean sense, if it is not matching, that means there is some bias. So you start calling it biased. Make sense? Any other question? Last, unbiased, unbiased? Standard deviation one? Yeah. So standard deviation, what I said is when you are computing the sample standard deviation, sample variance, let's say. So sample variance, the unbiased estimator of variance is 1 by n minus 1 summation of x minus mu whole square, not 1 by n. If you calculate sample variance using 1 by n minus 1 summation x minus mu whole square and take expectation of that, you will get the population variance. So that's why 1 by n minus 1 is an unbiased estimator of the population variance when you are doing it from sample variance. Okay. But for mean, the usual mean is an unbiased estimator. So that 1 by n minus 1 sometimes you see, and then you get confused. Why some place it is 1 by n minus 1, why some place it is 1 by n. For larger n, you then convince yourself it does not matter. I mean, that's what we all have done, right? That for 1000, it doesn't matter 1 by 1000 or 1 by 999. But it does matter mathematically. Statistically, it matters. Statistically, it matters because one is unbiased, other is not. Okay? Yeah.
Sir, I still don't understand why intuitively you would want to do why that.
Why?
Like intuitively.
Why will I want to drop out, right? Coming. I'll derive that now. So that's the next thing. Good question.
And also I think we discussed an innovation for ensemble feature, although I see some parallel.
There is parallel. There is parallel. So, okay, let me first answer it also from the ensemble point of view intuitively, and then we'll do the maths because it's the maths that will prove it. Intuitively, when does a model overfit? Think about all the things. Early stopping is one strategy talked about, right? So why early stopping is important? Because after a certain point, the model starts overfitting. So if you let the optimizer train the model long enough, it starts overfitting. So the idea is you should not let your optimizer train the model long enough. That's what early stopping is. Ensemble is also doing that in a separate way. It is saying you don't take one model, you take multiple models and train them. And hopefully if the number of epoch is same and not all of them will get overfitted, most of them will not. And in mean sense, it will be generalizing. Also, even if they are overfitting different data sets on different data sets. So in a mean sense, then it becomes a good estimate. Here also the same thing is happening. Here, because we are dropping off things, the model is actually changing from iteration to iteration. So that means no one model is getting the chance to get trained enough. In the same sense as early stopping, because it's not the same model that is getting updated, right? So not a single model is getting a chance to get itself trained enough number of times to be overfit the noise. This is the intuition. Now mathematically what is happening is something else actually. Mathematically we will now go there and we'll prove that this is actually equivalent to regularization. And that will prove mathematically. Okay.
But sir, not a single model is able to, like, it's kind of under because of a single model also.
It can. So again, statistically, right? You have 10 models, maybe 2 models are overfitting, 2 are underfitting. And then there are 8 models or 7 models that are reasonable. And also underfitting, overfitting is also not a global term, right? It is because in ensemble you are training the different data set, right? Subsample, a subset of data. So even if something is overfitting, it is overfitting that data set, not the other predicts data sets that, and each of these model is overfitting something else, right? Hopefully none of that is overfitting. That's the best case scenario, but in that sense. So that's why you see that when you take the mean, that is more like generalization, right? Because statistically each of them getting overfitted is very less probable. Okay. Okay. So this is an unbiased estimate, right? I thought I will complete this. I have 20 minutes. I have to be fast now. Anyways, so okay. So now equivalence between dropout and L2 regularization. Okay. And this equivalence will basically prove in case of a linear layer. Okay. Let's take a linear layer, same as before. Everything remains same. Okay. And let's see. So consider the same linear layer. Okay. And that means y is equal to summation wi xi y hat or y tilde, what I wrote, y hat. Y hat is equal to summation delta I wi xi, and we already know that the second is a wi tilde, and we already know that the second one is an unbiased estimator of the first one, so we know that, right? Now loss function. What is the loss function in the first case? So what is the loss function in the first case? Loss function without dropout. Without dropout. Let's take a single sample. If I take a single sample, it is t minus y square. I can put a half outside as well, but I'm not doing that. This is your loss function, right? What is the loss function in case of dropout? Can you tell me? It is little tricky, but let's see. Obviously, t minus y hat square is coming to your mind, but is that enough, or do you think there is something else? It has to be pro expectation, because remember that in each update, you are sampling this delta, right? So the loss function actually is getting changed because this delta is changing, getting changed. So this will be expectation with respect to delta t minus y hat whole square, and expectation is coming because delta is from Bernoulli with probability q, or rather because delta is random variable. Because at each step you are sampling a different delta. To account for that, you need to take the expectation of that. Okay. Now what we want to show is as follow. We want to show that this second loss function is actually the first loss function plus some regularization. And that regularization I am calling it, I'm claiming, spoiler alert, that it will be some form of L2 regularization. So what we want to prove is that the second loss function will give us something like the first loss function plus a regularization term. And that regularization term will be a L2 regularization, at least in some sense, is what I am claiming. Clear? Okay. So we need to work with the second one, right? So let us work with this. So we want to relate LD with L. That's what you want to do, right? And it's very simple. We'll take LD and do usual operation. Okay, let's take LD and see what we'll do. What was LD? Expectation with respect to delta, and then you have this term, the square term. I can open the square, a square plus b square minus 2ab, right? So t square plus y hat square minus 2 t y hat, right? Now expectation of summation is equal to summation of expectation, so the expectation will go inside. So what is expectation of t square? Is t a function of delta? T is target, right? My training data output. So it's not. So it's a constant. What is expectation of constant? Constant. So the first term will be t square. The second term obviously is a function of, and the third term is constant times y hat is equal to expectation of, sorry, constant time expectation of y hat. Expectation of ax is equal to a of expectation of x, right? So minus 2 t expectation of y hat, right? What is expectation of y hat? This you already know. This is equal to y. So the only term we need to work with is expectation of y hat whole square. Let's focus on that. So we focus on this term. Now expectation with respect to delta y hat square. What is it equal to? We used it, I think, last time somewhere. Variance plus expectation square. We used it in one of the last lectures. I forget which one, but why did we use it? What were we proving with this? We used it, but I don't remember where we used it. Anyways, I'll check. But I forgot where I used it, but we used it, I remember. Variance of delta. Right. Thank you. Yeah, initialization we used it, right? That plus expectation square of y hat. What is this term equal to? Y square, because it is expectation of y hat times expectation of y hat, y times y square. Now, so basically the only term that is remaining is variance, right? Let's focus on that. So variance y hat is equal to variance y hat is equal to what? Summation delta I w tilde I xi, right? Now w and x, are they function of delta? No. So they are constant. This delta is what? Whether a node will stay or not. And I said that the dropout is applied independently to each node. That means delta 1 and delta 2, they are independent. So that means there will no covariance of delta I comma delta j term will be there. So variance will basically go inside. So what will happen with this? What is variance of Ax? What is variance of Ax plus By where x and y are independent? Let's ask A square variance of x plus B square variance of y. Right? Variance of Ax plus By is equal to A square variance of x plus B square variance of y plus 2ab covariance of xy, that is 0. Right? So I'll write that also. So we know that variance of Ax plus By is equal to A square variance of x plus B square variance of y plus 2ab covariance of x comma y. This is something we study in our school, right? And if they are independent, the third term will go away. Okay. So in this case, they are independent. So this is equal to summation wi square xi square variance of delta I. What is variance of delta I? Where delta I is a Bernoulli distribution. PQ or so P times 1 minus P or Q times 1 minus Q. So this is equal to, let me write Q times 1 minus Q, but which is equal to basically PQ. Okay. And what is Wi square? Wi tilde square. Wi tilde is equal to Wi by Q. So this is equal to Wi square by Q square, right? Times xi square times Q into 1 minus Q. Okay. Or let's write it as P. So then what do I get? P by Q goes outside. It's for each I they are same, so they just go outside. Summation of Wi square xi square. Okay. Not a difficult derivation, right? It's pretty straightforward. So now you take these things, right? I'm boxing it. What will I take and where will I put? This is what we got. This I will go and put in this expression, right? And then this thing I will take and put into this expression. So let's call it equation 1, equation 2, and equation 3. So I substitute 3 into 2 and then 2 into 1, or substituting 3 and 2 into 1, whatever you call it, right? Substituting 3 into 2 and the resulting expression into 1. I substitute 3 into 2 and the resulting expression into 1. What do I get now? LD is equal to, so LD is equal to t square plus y square plus p by q summation wi square x I square minus 2 t y, right? Everyone follows what I did? And now what is it equal to? T minus y whole square plus p by q summation wi square xi square, right? What is this term? L. So the second term you can already see there is some wi square coming. So L2 regulation is on the way. It's a scaled L2 square because there is a xi sitting. So it's a scaled L2 square or generalized L2 square, actually L2 norm. L2. So this is generalized L2 regularization, and this you can also write as, so this one at least is equal to p by q, right? Yeah. W transpose W, where lambda is equal to diagonal of x1 square, x2 square, and how many inputs you have, right? It's a diagonal matrix. So if you do a product, what will happen? W1 times x1 square times W1, W1 square x1 square, W2 times x2 square times W2, W2 square x2 square, and you will get a summation of that, right? So this is known as Tikhonov matrix, which is basically weighted. It is basically weighing the weights, the regularization with respect to x. Okay. Now there are two more steps. I will not do that, but I will tell it verbally. In which way you can get the exact L2 regularization the way we know it. Now this loss was over what? One data, right? This was over one data. What happens when I have loss over n data? I do a average of that. So I do a average of summation I equal to 1 to n and that part, right? So the first term L will remain L. It will become summation I equal to 1 to n. So that's the L, the generalized L. Second term, Wi, does it depend on L, on the number of data? Wi does not depend on number of data. But what will happen to xi? Xi will now be summation over all the data. So it will become expectation of xi square. It will become expectation of xi square, right? And this Tikhonov matrix will become expectation of x1 square, expectation of x2 square, expectation of x3 square, and something like that, right? Now what if my data is normalized? If I normalize my data, then what is expectation of x1 square? 1. Expectation of x2 square 1, expectation of x3 square 1. So for a normalized data, and when you consider all the data, this Tikhonov matrix becomes identity matrix, and that's when you get the regularized L2 loss as you know it. I'll just write it. I did not do this derivation. Please do it on your own. If you have any problem, please feel free to meet me. I mean, it will be just 2 steps, but I'll write down what I just said. Okay, and we'll stop after that. So, considering all training data and assuming the data to be normalized lambda turns out to be an identity matrix, right? And this gives us regularized L2 regularized loss function. Okay. This part you should please do it on your own. If you have any doubt, feel free to come to me. So now you see mathematically what is dropout doing? It is basically regularizing it, and that's why it addresses overfitting. Okay. So I'll stop here. Thank you. We'll meet next time.